In this lecture, we are going to talk through the second law of thermodynamics. The second law of thermodynamics states that in any spontaneous process, there is always an increase in the entropy of the universe, like the whole universe. From this, we can take that so that pretty directly states that our irreversible processes that are spontaneous, we will see that the change in entropy will be greater than zero for the universe. Now, a reversible process will have an entropy change for the universe that's closer to zero, or equal to zero, and small for something that can go both the forward and the reverse direction. So no one direction is irreversible or spontaneous. And so let's look at what this entropy of the universe really means. This is a big idea. It's going to be defined pretty simply as just the entropy of your system and your surroundings together, for whatever the universe is. And so let's walk through this idea of the difference between our system and surroundings when thinking about whether or not something is going to increase the entropy of the universe, and therefore be spontaneous. And let's look at two things that do actually happen spontaneously, but with different changes in entropy for the system. Let's compare evaporation and condensation of water, since we've been spending a lot of time with water phase changes. So when water is evaporating, let's start there. Water is evaporating. We have our liquid molecules increasing in kinetic energy and becoming gas particles. That transition to the gas phase comes with a greater freedom of motion for the water particles. And what's happening is that our energy for Sorry. And what's happening is we're having our particles go from a more constrained environment to one with more freedom, with that increase in temperature and increase in kinetic energy. And so we're seeing matter distributed more evenly or more uniformly by increasing that motion. We're going to see the system, which is the water molecules, have an increase in entropy. So if water is our system, then our delta, our entropy change for that system should be greater than zero, because we're distributing matter more uniformly over a greater amount of space. We can also think about it as our water particles that are in the gas phase will have a greater increase, or will have a greater number of microstates available to it. So the final number of microstates for our gas particles is going to be greater than the number of microstates available to our water particles that are in the liquid state. And so our universe will have this positive entropy for the system. And as long as our surroundings isn't much more irreversible than our system, if it doesn't have a negative entropy that overwhelms it, we're going to see an increase in entropy for the universe, and we'll expect this to be a spontaneous process, which it is. And so that kind of matches really nicely with the way we were talking about this before of ice melting. So we talked about an expected increase in entropy for the system as you go from a solid to a liquid to a gas because of that increase in motion, or freedom of motion. But we then also stated that the opposite of that should see a decrease in entropy for the system. Let's think about condensation. Again, here our water is equal to the system, And we're going from the gas phase to the liquid phase. And so we're reducing the actual freedom of motion that our water particles actually have. And so our number of microstates in the final liquid are going to be less than the microstates available to the initial gas water particles that exist in the sample. So our change in entropy for this system should actually be less than 0. It should be negative. And so if we were looking at this through the lens we were using prior to introducing the second law of thermodynamics, we would see a decrease in entropy, and we would say, well, this condensation process probably isn't spontaneous, because we were seeing a correlation between spontaneous processes and an increase in entropy. And so by using an evaluation of the entropy of the universe rather than just the entropy change of the system, we'll have a better way of evaluating whether or not a process should be spontaneous. Because you can have a spontaneous process that actually has a negative value for entropy for the system, like condensation. And the way we can explain this is that the enthalpy of the surroundings is very positive and larger than the entropy of the system. And that overwhelms this negative entropy of the system and creates an overall increase in the entropy of the universe. And what's happening with our surroundings here in this exothermic process is that, or in this, I gave it away, in this spontaneous but negative entropy process, is that as our gas particles condense to liquid, they release heat or energy into the surroundings. And we've talked about phase changes as being either endothermic or exothermic. And so this is an exothermic phase change where energy is released, kinetic energy is released as heat. So that way our water particles can actually slow down and have less motion. That means that the entropy of our surroundings is going to increase as energy is distributed more uniformly, or heat is distributed more uniformly. And so that allows us to have a spontaneous process that doesn't actually have increase in entropy for our system. And this is going to encapsulate that with a lovely graph. If we think about entropy and compare it for the universe, system, and surroundings, in the case where we have a negative entropy for the system, like when our gas is condensing into a liquid, we need to have an entropy of the surroundings that is positive and also larger. So that way we can have an entropy for the universe that has an overall positive charge, because that's just going to be the sum of this system and surroundings entropy. So that brings us to this idea or summary that if the entropy of the universe increases, that is actually when we have a spontaneous process. When the entropy of the universe decreases, we have our non-spontaneous process. So rather than thinking of entropy change for the system itself, we need to evaluate both the system and the surroundings and come up with a sign or a positive or negative increase or decrease for the universe. Again, now we've also talked about things being at 0. So if the entropy of our universe ends up being 0, that's when we're going to be at one of these reversible processes. Our system will be in equilibrium. and it can go either way. So let's look at this again for something that's spontaneous, not spontaneous, and at equilibrium. For our process that is spontaneous, so we'll have entropy for the universe that increases. I want to use our examples of heat flowing. If we are showing heat flowing from a hot object to a cold object, we have let's define our system as the entity the heat is flowing from. So our system and our temperature of our system is going to be greater than the temperature of our surroundings, which are colder. So let's look at the actual entropy of these systems. Remember that entropy is really equal to the heat of that reverse process divided by the temperature. And so for our system, that entropy is really going to be the heat of the reverse divided by the temperature of that system, which is larger, remember, than the surroundings. And then if we think about what Q is, that's really just heat, right? That's from back when we reviewed thermochemistry. It's like, so if heat is greater at our system and it's being lost, then we're going to see a loss of heat and a gain of heat to our surroundings. And so with this system temperature being larger and this negative value on the heat, we can expect that the change in enthalpy for our system is going to be less than the change in enthalpy for our surroundings. And this is going to lead us then to enthalpy for our universe that's positive and therefore spontaneous. Now let's take a look at a process where we imagine heat is flowing from a cold object to a hot object. We expect this to be a process that is not spontaneous. So the entropy of the universe should be less than 0. So again, we're going to keep our definitions the same. We've got our system and our surroundings. And our temperature for our system is again greater than the temperature of our surroundings. The amount of heat that flows, let's consider it the same. And so that heat of that's being transferred divided by the temperature of our surroundings should itself still be greater, if you think of the absolute value, than the heat that's flowing divided by the temperature of the actual system. But in this case, the hot part of the system is actually gaining heat. So we're going to have the positive sign now for Q, where surroundings is losing heat at that lower temperature. And so the general entropy change for the system is still going to be less than the entropy change for the surroundings, just based on the magnitude of our temperatures. But these signs in front of our heat are going to change the actual sign of our entropy of the universe calculation. We're going to end up with a change in the entropy of the universe that's actually negative. And so that supports this idea that heat flowing from a cold to a hot object is something that should not be spontaneous. Now, in the case where the temperature difference between our system and surroundings is very, 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 very small, such that we can actually think of these as being about equal, then there is going to be a thermodynamically reversible heat flow between the two. In this case, the difference is just too small that our magnitude of change between our entropy of our system and the entropy of our surroundings will be small enough that we will calculate an extremely small entropy of the universe that is essentially 0. And so heat should be able to flow back and forth between these objects at equilibrium. In general, when we're looking at the entropy of the universe as a sum of the system and the surroundings entropy, we find that it's reasonable to substitute or approximate this heat of the reverse process with the heat of the surroundings. And so we can say the entropy of the surroundings is really equal to the heat of the surroundings divided by the temperature. And we can substitute it into this equation here. And our surroundings is what we do this with the most. With the system, we really think about it still as the heat of that theoretical irreversible process, if it was reversible. So here's an example I want to use that with. And this is looking at calculating the entropy change for the surroundings. And we're at 25 degrees Celsius, so we can just right away convert that to 298 Kelvin for the combustion of propane below into carbon dioxide and water. We're given an enthalpy, which we haven't used yet, of a reaction. And so take a look at this, pause the video, and try it on your own or see where this is going. And I'm about to walk through the solutions here. Okay. So looking at this problem, I think I'd first like to think through what it is that we're being asked to find, and that is that entropy change in the surroundings. And so the entropy change in the surroundings, we can approximate as the heat of the surroundings divided by that temperature. And we've got temperature already. That's our 298 Kelvin. That'll be what we use for T. And so now the question is, what is this heat of the surroundings? That's the piece that we need. Well, we're given the enthalpy of a reaction, which is really the enthalpy of the system, if we're thinking about this in terms of just system versus surroundings. And this is getting back to a chemical reaction taking place inside a solution or even on its own, as being the system itself and the surroundings being the solution or the air or the container that it is in. So I can say that this enthalpy of the system is negative 2,044 kilojoules. Now, if you can remember back to our thermochemistry, if not, I recommend looking at the review slides that are available. The heat of the surroundings was always the opposite of the heat of the system. So the amount of heat that flowed from the system to the surroundings would be the amount that the surroundings increased, or the other way around. So they're just opposites of one another. And so in that case, we can say that if we have the enthalpy of the surroundings, it should be equal to the negative of the enthalpy of the system. Remember, enthalpy is really about heat flow, about heat leaving or coming into a system that's endothermic or exothermic. And so we can equate these two together. And I'm going to go ahead and say that the enthalpy of the surroundings can be approximated with, the entropy of the surroundings with that enthalpy of my surroundings divided by the temperature of the system. And that then, based on this equality we talked about here, is the negative of the enthalpy of my system divided by temperature. And if we backtrack again, that really is the opposite, or the negative, of the enthalpy of the reaction. Oh, sorry, it all came at once. Over temperature. And now I have something I can solve with what I have in my problem. So my enthalpy of the surroundings is going to be equal to the negative of negative 2,044 kilojoules divided by the temperature of my system, which is 298 Kelvin. And if I plug this in, I'm going to get 6.86 kilojoules per Kelvin. And if you want to put that in joules per Kelvin, it would be 6.83 times 10 to the third joules per Kelvin. So I've got right here a positive value for my enthalpy of the surroundings, or my entropy of the surroundings. So the entropy of my surroundings has increased. Does that make sense? Well, remember, we're looking at a combustion reaction. And a combustion reaction of propane, that's what I use to cook my food. So a positive entropy of my surroundings makes sense because heat is flowing from my reaction to the surroundings, and it is being distributed uniformly into my surroundings. Which is equated to an increase in the microstates from my reaction to the actual surroundings for that energy. Rather than looking at matter, this is looking at energy. And so that makes sense for an exothermic reaction. I expect the entropy of the surroundings to increase significantly as heat is distributed uniformly throughout it.